is complex numbers. So we're going to perform different operations in I form, and then we're going to use complex conjugates to help us find the quotients of two complex numbers. So starting off the imaginary unit I actually stands for the square root of -1. Okay, so because we can't take the square root of a negative number, but imagine if we could, then we call that I. So if we're trying to take the square root of a negative number, so let's let C be any number, for instance, 36. Then we can rewrite this. Under the radical, we have a 36 times the square root of 36 times -1. So following our radical rules, we can take and split this up as the square root of 36 times the square root of -1, which we know that the square root of 36 is just 6, and the square root of -1 stands for I. So this is imaginary form. This is the imaginary number 6I, and it's equivalent to the square root of -36. So let's try to write this radical in I form. And if it's a negative underneath the radical, it will always have an I form. So I'm going to break this up into the square root of 16 over 25, the positive version, just times a -1. Okay, and that's all underneath the radical. So I have a division problem here. I can rewrite this as the square root of 16 over the square root of 25, and then times the square root of -1. Okay, I'm going to give the square root to everything underneath the radical. The square root of 16 is 4, the square root of 25 is 5, and the square root of -1 is I. So 4/5 I is the imaginary form for the radical in part B. Part C, I'm going to do the same thing. Now, as you get better at these, you're not going to have to write out every step. For instance, I already know it's going to be like the square root of 54 times the square root of -1. So I'm just going to write this as the square root of 54 times I. But I need to break down the square root of 54. So I'm looking for perfect squares in 54. I know 9 is a perfect square, and 9 times 5 would give me, 9 times 6 would give me 54. The square root of 9 is just 3, and I can't break the square root of 6 into any more perfect squares. So actually 54 can just be written as 3 square roots of 6. Remember, I want to simplify this radical, so I have 3 square roots of 6 times I. And actually in Algebra 2, they're going to want you to write the I in front. Since it doesn't have a house, everything that doesn't have a house needs to go in front. So the 3 times the I, and then times the square root of 6. So this is in I form because there is no more negative underneath the radical. Down below, up top, I have the square root of 48 times the square root of -1, which would just be I. Down below, I have the square root of 3 times the square root of -1, which would just be I. Notice that I have an I in the top and an I in the bottom. Those are going to cancel. They divide out. I divided by I is 1. They're not there anymore. So notice that I have the square root of 48 over the square root of 3. So I'm going to combine that into one square root because I do notice that 48 divided by 3 will simplify to 16. So the square root of 16 is just 4. So there is no imaginary part here. So just because you start with a negative radical doesn't mean you're going to have an I in your answer always. All right, operations with square roots of negative numbers. So those square roots of negative numbers, now we're going to try to add and subtract and multiply them. But before we can do that, we must first write them in I form. Writing them in I form is taking away the negative underneath the radical, and you're going to get something looking like this. So that first page was writing in I form. So let's say we have an AI plus BI, which means I'm going to add my A with my B and keep the I there. It's kind of like combining like terms. So for instance, when I had like a 7x plus a 3x, these were like terms and they combined to be 10x. So the same thing here, if I have a 7i plus a 2i, I'm going to add the 7 with the 2 and get 9 and keep the I there. Same thing for subtraction. Right here is subtraction, this was addition. And then we have multiplication rule. Let's say we have 7i times 2i. That means we're going to multiply our numbers. 7 times 2 is 14. And then we're going to multiply our i's. I squared is what we'd get. I times I. I want you to look over here at this study tip. It gives us the powers of I. We know I to the first is just I, but I to the second power, this one's important. I to the third power you'll probably see, and I to the fourth you'll probably see. Fifth, sixth, seventh, and eighth, they're listed here. But they may not be as frequent. You may not see them as often. But I squared is definitely the most popular one that you're going to see. I squared is equivalent to -1, and here's why. So I squared means, well, first of all, I means it's the square root of -1. So you have I and you're squaring it. So that's I and you're squaring it. Well, a square root and a square, they cancel. So you're just left with -1. So down here, 14 times I squared is basically 14 times -1. So a final answer of 14. So those are some of our rules for operations with I form. So for instance, let's start with A. Before we can add these square roots with negative radicands, I need to put them in I form. So I have the square root of 9 times I plus the square root of 7 times I. Well, the square root of 9 is just 3, so I get 3i. And I can't take the square root of 7. I can't break it down anymore. So I just get, I'm sorry, back up. Oh boy. I get the square root of 9 times I plus the square root of 49 times I. Okay, the positive version times I, because that was the square root of 49 times the square root of -1. The square root of -1 changes to I. So this would simplify to 3i, and this would simplify to 7i, since those are perfect squares. Now I'm going to add. Remember, if they are adding terms with I, we can add their coefficients. So 3 plus 7 is 10. 10 i's would be my final answer. Over here, I want to put them in I form before I can subtract. So I have the square root of 32 times I minus 2 square roots of 2 times I. All I did here was change the negative square root of 2 into the square root of 2 times the square root of -1. The square root of -1 is I, and then I have that 2 out in front. So from there, I need to simplify. The square root of 32 needs to be broken up into perfect squares. So I have the square root of 4 times the square root of 8. Square root of 4 is just 2. 8 can be broken up into the square root of 4 times the square root of 2. The square root of 4 is 2. So I have 2 times a 2, which is 4, times the square root of 2. So my final simplified radical is 4 square roots of 2 for 32. So I have 4 square roots of 2, and then I have this I. I'm going to write the I in front so I don't forget about him. Over here, I have 2 and an I outside a house, and then a square root of 2 in a house. Everything outside a house needs to go in front of it. So remember, if I have a radical and I'm trying to subtract radicals, I need to make sure they're alike. So anything underneath the house needs to match, which it does, it's 2. And then it needs to be the same index. So it's squared and squared. So I can actually subtract these. So look at their coefficients. I have 4i minus 2i. I'm going to subtract those and leave it as a square root of 2. So once I do that, 4 minus 2 is 2i square root of 2 for my final answer. Part C. In part C, we're multiplying. So what we got going on here is the square root of 15 times the square root of -1, which would be I. And same thing over here, I square roots of 15. So if it's times itself, basically isn't that squared? So it's I square roots of 15 squared, which means we're squaring the I and we're squaring the square root of 15. Well, the square root of A 15 cancels with the square, so you have 15 times I squared. What is I squared? Oh yeah, let me check back in my notes. It's -1. So it's 15 times -1 for a final answer of -15. Over here, I need to do some foiling, but first let's put it in I form. So I have the square root of 5 times I. So let's write I in front and the square root of 5 times everything in here. So I need to break this up. It's going to end up being the square root of 45 times I. So I need to break up the square root of 45. And let's do that off to the side. I'm looking for perfect squares, so that'd be 9 and 5, which breaks up into 3 square root times square root of 5. So I have 3 square roots of 5, but don't remember it was a negative, so I have that I there. Okay, and then over here, it's going to be the square root of 4 times the square root of -1, which would just be 2I. Okay, so this is minus 2I here. And then we need to distribute. So I'm taking I times the square root of 5 times 3I square roots of 5. So I'm going to multiply everything outside the house. So I have 3I times I, that's I times I squared. Then the square root of 5 times the square root of 5, which would be the square root of 25. I'm going to distribute again over here. So I have I times 2I, which would give me 2I squared. In the square root of 5, there's no other radical, so I just tack it on. Now I'm ready to simplify. Remember, I squared is the same as -1. So I have -1 times 3, which is -3. Then the square root of 25 is 5. So 5 times -1 times 3 would be -15. Over here, I squared is -1. So times 2 would be -2 times the square root of 5. So it's minus the -2 square roots of 5 minus a negative is like plus a positive. So my final answer is -15 plus 2 square roots of 5. I cannot combine those. Those are not like radicals. If you have a radical, you can't add it with anything else unless it matches the exact same radical, which is why we could subtract it up here. If these radicals matched, we could subtract their exponent, but I don't have a matching radical, so I cannot add these, and that's all the further I can go. All right, complex numbers now. So we talked a little bit about imaginary numbers. Imaginary numbers have the I in them, but complex numbers have a real number and an imaginary number. So them combined, it makes complex. So it's a mixture of the two. The A is the real number part, and the BI is called the imaginary part. So it has both real and imaginary. If we're going to add or subtract two complex numbers, we need to add and subtract the real and imaginary parts separately. So it's basically, again, like combining like terms. So here's a complex number, A plus BI, and we're adding it with another complex number, C plus DI. So what you want to do is collect all of the real numbers and add them together, and collect all of the imaginary numbers and add them together, keeping that I with it. Same thing for subtraction. You're going to take the A minus the C and then the BI minus the DI. Collect those like terms. So for instance, if we're adding and subtracting these complex numbers, in part A, remember, we're going to sort of collect our like terms here. So we have a 3 plus a -2, which would give us 1. And then we have the I term. So we have a -I plus a positive 4i. So a -1 and a positive 4 would make 3 i's there for my final answer. Down here, same thing. I'm going to try to collect my real numbers, go in the front. So I have a positive 5, and that would just be on its own. But then I have my I term, so I have a 3i plus a negative 3i, which would actually cancel. 3 minus 3 is 0, so my answer here would be 5. Down here, I need to be a little bit careful when there's subtraction. What I like to do is sort of distribute my subtraction. So it's a negative 1 times a negative 1, which would be a positive 1. A negative times a positive 5 would be a negative 5i. And then plus 7 plus 2i. So now go through and find all your real numbers. So 4, 1, and 7 would combine to be 12. And then find your I terms. A negative 5 and a positive 2 would be a negative 3i. Okie doke. Down here, I have, again, subtraction. I have a square root of a negative number, a square root of another negative number. So before I do anything, I want to put them in I form. So I have the 6 plus 3i, that's good. That's a complex number right there. I want to change this into a complex number. So the 2 is fine, but the square root of negative 8, so maybe you want to do that off to the side. Square root of negative 8 is the same as the square root of 8 times the square root of negative 1, which would be an I. So I have I times the square root of 8. The square root of 8 can be broken down into the square root of 4 times the square root of 2. The square root of 4 could be broken down into 2. So the square root of 8 is an I and a 2 and a square root of 2. So 2i square roots of 2. And then I'm subtracting the square root of negative 4. Again, you may want to do that like off to the side somewhere. The square root of negative 4 is the same as the square root of 4 times the square root of negative 1. The square root of negative 1 is I, and the square root of 4 is 2. So over here, I have a minus 2i. So now collect like terms. If you see there's a 6 and a positive 2, those are the real numbers, so that would give me 8. And then look at your I numbers. You have a 3i, a minus 2i square roots of 2, and a minus 2i. So if we are, let's put that all in parentheses, a 3i, a minus 2i square roots of 2, and a minus 2i. So collecting even further, this has a radical. I can't subtract because no other things have a radical, but the 3i and the 2i can combine. So 3 minus 2 would be 1i, or sorry, 1. Yeah, 1i. And then the rest would have to be on its own. I would leave it like this. The book might want it a different form because remember a complex number is in this form where it's a number times I. So if we want to essentially factor out an I, this would be 1 minus 2 square roots of 2i. So this is my number times I. This is actually the correct form, but if you got to this step, like on your test, I'd count it correctly. But this is the complex form of that. So ask me if you have any questions on this slide. Complex conjugates. So the same idea of a conjugate from previous chapters we can use on complex numbers. So a plus bi is a complex number, and a minus bi are called complex conjugates. Remember, the only thing that changes is the addition and subtraction side. So if we multiply two conjugates, like right here, if we actually FOILed it out, it's big, long, and complex. But what I want you to remember or know is that the end result is the same thing as squaring the A and squaring the B. Notice that there is no more I. Okay, you're starting with a conjugate of complex numbers and you're multiplying them, and look at what you end up with. No more I. A squared plus B squared. So for instance, if I were to multiply these two conjugates, 4 minus 5i and 4 plus 5i, I'm squaring the 4 and I'm squaring the 5. There is no more I. So 4 squared is 16 plus 5 squared, so 25. You get 41. Notice that all of these conjugates, complex conjugates multiplied by each other, just result in a number. There's no more I. So here, this is the last slide. We use this idea of conjugates, remember, to help us rationalize and to help us simplify. So if I am writing this quotient, it's 2 minus I over 4i in standard form. Remember, what we want to do is multiply by the denominator over itself. And not just the denominator, but the conjugate. Okay, so the conjugate of 4i, if you want to think about it this way, 0 plus 4i is what we have going on here. So the conjugate would be 0 minus 4i. So technically, the conjugate that we're going to be multiplying by is negative 4i. And we need to do it in the top and in the bottom so it doesn't change our problem at all. All right. So let's look at our denominator. The conjugate multiplied by itself. So I have a 4 times a negative 4, which would be negative 16, and I times an I, which would be an I squared. Up top, I'm sort of distributing this to each item. So a negative 4i times a 2 would be a negative 8i, and a negative 4i times a negative I would be a positive 4i squared. And let's just keep simplifying. Negative 8 times I can't simplify, but I squared, I know that's a negative 1, so that would change that to a negative 4. And in the bottom, I have all right, for problem B, you need to multiply by the conjugate. So instead of the minus, you just change it to a plus. And if you do it in the bottom, you have to do it in the top. Oops. So 4 plus 2i. And then we want to make sure that in the top we FOIL. So first, 2 times 4 is 8. Outer, 2 times 2i would be a positive 4i. Inner, 4 times 3i would be 12i. And then last, 3i times 2i would be 6i squared. That's in the top and in the bottom. Since I'm multiplying two conjugates, remember the rule is it's the first number squared, so 4 squared. And then a plus is the rule, and then the second number squared without the I. So the second number is 2, so I'm going to square it. I'm going to simplify the top. I have 8. Collect these like terms. So 12 plus 4 is 16i. And then 6 times I squared, remember I squared is negative 1, so negative 1 times 6 is negative 6. Down below, 4 squared is 16 and 2 squared is 4. Keep simplifying because I can combine the 8 and the negative 6, so I have 2 plus 16i. And then in the bottom, 16 plus 4 is 20. I'm going to break this up so that I can simplify it and put my real numbers in the front and imaginary in the back. It can't be all one. And like I did over here, I put the real in the front and imaginary in the back. So 2 over 20 plus 16i over 20. 2 over 10, divide them each by 2, I get 1/5. Oops, I'm at 1/10. 16 divided by 20 divided by 4, so you get 4/5. If you have questions about conjugates, please let me know.